Well, it is a tragedy that continues to fascinate. After more than a century, the Titanic hitting an iceberg and sinking in April 1912.
Is it possible to return the Titanic to the surface after more than a century in the depths of the ocean? What once seemed like an impossible dream could now become a reality thanks to scientific advances and revolutionary technologies. From gigantic, inflatable balloons to innovative methods like using liquid nitrogen to freeze the wreck, experts are rethinking what we thought we knew about recovering historical remains. In this fascinating journey, we will explore the boldest and most ingenious approaches that could bring back one of the greatest icons in maritime history. Could the Titanic return from the abyss and reclaim its place in history, this time out of the water? Stay with us as we unravel the most surprising plans to rescue this legendary ship and what it could mean for science, technology, and our connection with the past. Number 10. Submersible cranes. The proposal to use submersible cranes to recover the remains of the Titanic is undoubtedly one of the most innovative and audacious ideas in the field of underwater engineering. These cranes, designed to operate at extreme depths, would represent a true technical feat, combining the brute strength needed to lift such a colossal structure with the precision required to avoid destroying what remains of the iconic transatlantic ship. However, implementing this technology not only presents exceptional technological and logistical challenges, but also raises ethical and historical preservation concerns. To begin with, the depth at which the Titanic lies, more than 12,500 feet, approximately 3,800 meters, below the surface of the Atlantic Ocean, represents an extremely hostile environment for any type of human or mechanical equipment. At that depth, the water pressure reaches 5,500 psi, pounds per square inch, a force strong enough to crush almost any conventional structure. For this reason, submersible cranes would need to be constructed with materials of the highest strength and specialization, such as titanium alloys or steels, specifically treated to resist corrosion and extreme wear. Key components of the cranes, including electric motors, hydraulic pumps, and the crane arms themselves, would have to be designed and manufactured with such precision that they could withstand not only the water pressure but also the near-freezing temperatures of the ocean at such depths. The technical challenge is not just limited to material strength, it also extends to the need to operate with unprecedented precision and delicacy. The Titanic, after more than a century at the bottom of the sea, is in an extremely fragile state. Corrosion has weakened its hull, and the decks have suffered partial collapses, making any attempt to handle its remains an extremely delicate task. Submersible cranes would have to operate in an extremely controlled manner to avoid further damaging the wreck. The choice of attachment points would be crucial, as it is necessary to avoid generating uncontrolled tensions that could fracture or disintegrate parts of the ship. This would require millimetric control of the crane movements, something that could only be achieved with advanced sensor systems that monitor in real time the stability of the wreck while the lifting operation is underway. A fundamental aspect of this process is the impressive weight of the Titanic, which exceeds 46,000 tons. To lift a load of this magnitude, the submersible cranes would need to have an absolutely exceptional lifting capacity, far greater than the most powerful cranes currently in use, even those handling the transport of large ships or Nimitz-class aircraft carriers. This would mean not only the ability to lift extraordinary loads, but also the need to combine this strength with real-time adjustment of the movements. The lifting systems would need to be equipped with dynamic control technologies that responded immediately to any changes in the stability of the Titanic structure, adjusting the distribution of the forces applied to prevent the ship from disintegrating under the pressure of the operation. Although the possibility of using submersible cranes to lift the Titanic is technically feasible, their development and deployment would involve a monumental investment in terms of resources and knowledge. The technologies required to create equipment of such capacity would push the limits of current ocean engineering, demanding advances in areas such as underwater robotics, handling large loads in extreme conditions, and real-time monitoring of complex environments. Added to this is the inherent risk of causing irreparable damage to the Titanic during the lifting process, which raises serious doubts about the viability of this option as a way to recover the wreck without sacrificing the historical and cultural heritage represented by the famous ship. This approach, while technically fascinating, presents a series of challenges that require careful consideration, not only from an engineering perspective, but also from an ethical one. The possibility of irreversibly damaging a historic icon like the Titanic while attempting to recover its remains is a significant risk that must be assessed with the utmost caution. Number 9. Cable lifting. Among the more direct and seemingly simpler methods to recover the Titanic is cable lifting. This approach proposes using giant cranes mounted on surface vessels to lift the wreck using high-strength cables. However, while the concept is simple in theory, the challenges it presents are immense, especially when dealing with such a large, heavy, and fragile object like the Titanic. To begin with, the cables used would have to be incredibly strong and resistant to corrosion. Advanced materials such as ultra-high molecular weight polyethylene would be necessary to support the weight of over 46,000 tons while withstanding extreme pressures and corrosive conditions at the seafloor. In addition, these cables would need to be flexible enough to maneuver around the Titanic's remains, but strong enough to prevent breaking during the lift. The use of cranes also involves an unprecedented level of power and load capacity. The largest cranes in the world, mounted on heavy lift vessels, would have to work in tandem to distribute the load evenly between the Titanic's bow and stern, which are separated and structurally weakened. Attaching the cables securely to both parts of the wreck would require the use of advanced underwater robots and technical divers, who would have the difficult task of identifying the strongest points for attachment. This is critical, as any failure in the attachment points could cause the sections to break apart during the ascent. Another major challenge is synchronizing the lift. The cranes must lift the cables at the same speed and with the same force to avoid uneven tensions that could fracture or deform the wreck. Even a small difference in lifting rates between the cables could cause imbalances that would jeopardize the integrity of the Titanic. This level of precision requires constant monitoring and real-time adjustments using advanced sensors and automated control systems to ensure uniform movement. In addition to the technical challenges, the fragility of the Titanic adds an extra layer of complexity. After more than a century on the seabed, the wreck's structure is severely compromised by corrosion and bacterial action. Lifting it without causing further damage would require an extreme level of care, making this operation one of the most delicate and complicated ever attempted. Despite the barriers, cable lifting remains one of the most discussed options due to its conceptual simplicity. However, the combination of enormous technical challenges, the need for absolute precision, and the risks associated with the Titanic's fragility make this method as difficult to implement as any other. Number 8. Mass displacement. A unique proposal to recover the Titanic suggests making it lighter, allowing it to float by itself. This method is based on pumping expandable foam into the hull and compartments of the wreck, displacing the water and reducing the overall density. If the Titanic is made less dense than water, it could rise from the depths following the principles of buoyancy. However, while the physics behind this concept are simple, the execution faces immense logistical and technical challenges. The expandable foam, typically made from polyurethane or isocyanurate, contains cells filled with inert gas that allow it to float. In theory, injecting enough foam into the Titanic's compartments could provide the buoyancy necessary to lift its colossal weight of 46,000 tons. But transporting the enormous amount of foam required to the wreck site, over 12,500 feet underwater, represents a major obstacle. The foam components would need to be mixed in real time and pumped through reinforced hoses capable of withstanding the extreme pressures of the ocean floor. Installing the foam injection network within the wreck also poses risks. The Titanic's interior design is a labyrinth of compartments and hallways, many of which are collapsed or blocked by debris. The foam must be carefully distributed to fill the empty spaces without accumulating excessively in certain areas, which could generate uneven pressures and damage fragile bulkheads. Sonar scans and detailed maps would be crucial to identify the ideal injection points, and the process would require constant monitoring to ensure that the foam is distributed evenly. Another major challenge is controlling the Titanic's ascent once the foam has provided sufficient buoyancy. A rise that is too fast could create structural stresses that fracture the hull or cause further collapses. To avoid this, the foam injection rates and resulting buoyancy would need to be adjusted carefully, allowing for a gradual and controlled ascent. This process would be overseen by a team of experts from the surface, using sensors to monitor pressure and the wreck's stability in real time. Although alternative methods have been proposed, such as using wax or ping-pong balls to displace the water inside the hull, these also face limitations. Wax could solidify in the pipes during transportation, and ping-pong balls would implode under the extreme pressures of the seafloor. Furthermore, none of these materials could be distributed as evenly inside the wreck as expandable foam could. Despite its challenges, mass displacement with foam remains an innovative idea that combines simple buoyancy principles with modern technology, although its practical implementation still seems far from achievable. Number 7. Lifting the Titanic with buoyancy tanks. Lifting the Titanic from the depths of the North Atlantic, over 12,500 feet underwater, has fascinated humanity for more than a century. One of the most intriguing proposals to recover this iconic wreck is the use of buoyancy tanks. This approach is based on the idea of attaching large containers filled with compressed air to the Titanic to generate the upward force needed to bring it to the surface. Although the theory behind this method seems logical and relatively simple, the actual implementation in the extreme environment where the Titanic is located represents a monumental technical and logistical challenge. To understand the challenges inherent in this proposal, it is crucial to consider the magnitude of the Titanic. With its 46,000 tons of weight and 882 feet in length, the Titanic is not just a wreck, but a colossal structure situated in an extremely hostile environment. The pressure at more than 12,500 feet depth reaches approximately 5,500 psi, pounds per square inch, a force sufficient to destroy almost any conventional material. Therefore, the buoyancy tanks used to lift the Titanic would need to be made from ultra-resistant materials such as titanium alloys or advanced composites. These tanks must not only withstand the crushing pressure of the ocean floor, but also resist saltwater corrosion over an extended period. Every component of this system would need to be rigorously tested to ensure its reliability under such extreme conditions. One of the most significant complications of this method is that the Titanic is not located in a single intact piece. After more than a century on the ocean floor, the wreck is divided into two large sections, the bow and the stern, separated by approximately 2,000 feet of debris. This separation means that instead of applying buoyancy evenly, the tanks would need to be distributed along the two main parts of the ship. The challenge here is that buoyancy must be applied perfectly balanced to prevent the sections from moving or fracturing due to uneven lifting forces. If the flotation is not distributed correctly, it could cause the Titanic to break further, compromising its already weakened structure and ultimately making it more difficult to recover. The installation of the buoyancy tanks would, in itself, be a monumental task. To place the tanks on the Titanic, remotely operated vehicles, ROVs, would need to be used. These vehicles would have to navigate through the wreckage of the Titanic, maneuvering in low visibility conditions in an environment with near-freezing temperatures and unpredictable ocean currents. The ROVs would be responsible for precisely attaching the tanks in the most strategic areas of the wreck. However, this would only be possible with the help of highly trained divers who would need to perform meticulous tasks at extreme depths, a challenge that is not only technical but also human. The extreme conditions in which they would have to operate, combined with the fragility of the Titanic's remains, make this task extremely dangerous and difficult. Once the tanks are attached to the Titanic, the next step would be to fill them with compressed air to displace the water and create the necessary buoyancy. This process requires colossal infrastructure on the surface, including large ships equipped with high-capacity compressors. These compressors would send air through miles of pipes to the seafloor, where the tanks would be located. While this may seem relatively simple in theory, any failure in the pipe system or compressors could destabilize the entire process, putting the recovery operation at risk. Additionally, the Titanic could become trapped on the ocean floor if the air is not pumped in a controlled manner, or if any part of the system is affected by the extreme environmental conditions. Precise coordination between the various components of the operation, which would include underwater teams, surface technicians, and divers, would be essential to prevent any unforeseen circumstances that could result in irreversible damage to the wreck. Although the use of buoyancy tanks is technically possible, its implementation in the case of the Titanic remains an unprecedented engineering feat. The colossal resources required to carry out an operation of such magnitude, combined with the complexity of the extreme conditions and the wreck's fragility, make this one of the most ambitious and difficult solutions that could be attempted. Additionally, the possibility of causing irreversible damage to the Titanic during the recovery process raises serious doubts about the feasibility of this approach. Meticulous planning, cutting-edge technology, and a multidisciplinary team of experts would be essential to overcome these obstacles. But even with all this, the risk of causing further damage to the Titanic remains a considerable challenge. Number 6. Hydraulic lifting system. The use of a hydraulic lifting system to recover the Titanic is a proposal that, in principle, leverages modern technologies to tackle one of the most complex challenges in underwater engineering. This approach involves installing large hydraulic jacks beneath the wreck, anchoring them to the seabed, and using high-pressure hydraulic fluid to slowly raise the ship to the surface. While the idea is based on sound technical principles, the challenges involved in its implementation are so monumental that they cast doubt on its feasibility in the context of recovering the Titanic. One of the first and most evident problems is the extreme pressure the hydraulic jacks would face. At more than 12,500 feet deep, the water pressure reaches 5,500 psi, which represents a significant challenge for any type of equipment designed to work at such depths. The hydraulic cylinders needed to lift the Titanic would have to be massive and made of advanced materials, such as titanium alloys or high-strength steel. These cylinders would need to withstand not only the high pressure, but also the low temperatures near freezing, which makes the design of the hydraulic systems even more complex. Furthermore, the steel plates used to distribute the loads along the Titanic's hull must be placed with precision, as any misalignment could create concentrated stresses that could further damage the ship's structure. The challenge of positioning the hydraulic jacks is another critical point of this system. The Titanic is not intact, and its wreckage is scattered and partially collapsed. This means that to distribute the lifting forces evenly, an exhaustive analysis of the wreck's structure must be conducted to identify the most suitable support points. A mistake in the placement of the jacks could cause fractures or even the collapse of the more fragile sections of the hull, such as the bow or stern. Additionally, the Titanic is positioned and oriented in a way that could complicate the proper alignment of the jacks, which would further increase the risk of damaging the structure during the lifting process. One of the most complicated features of this approach is the precise synchronization of the hydraulic jacks. To prevent the Titanic from tilting or braking during its ascent, each jack must extend at the same speed and apply the same amount of force. This requires an advanced control system that can monitor and adjust the hydraulic pressures in real time. Even the slightest error in the calibration of the cylinders could compromise the Titanic's stability during the lifting process. The desynchronization of the jacks could destabilize the wreck, increasing the risk of it fracturing or sinking even further. In addition to the technical challenges related to pressure, materials, and synchronization, the extreme conditions of the seabed present additional obstacles. Total darkness and low temperatures make the installation and maintenance of the hydraulic jacks incredibly difficult. The accumulated sediments on the seabed can interfere with the positioning of the equipment, making the work of remotely operated vehicles, ROVs, which would be necessary to install the jacks in the correct locations, even more complex. These vehicles would have to maneuver in a difficult-to-access environment, with unpredictable ocean currents and virtually zero visibility. On top of all this, there is the need to operate in a hostile environment with temperatures near freezing, which could affect the performance of the equipment and increase the risk of mechanical failures. As for the infrastructure required to carry out this operation, not only would specialized submersible vehicles and hydraulic equipment be needed, but also surface support vessels capable of supplying hydraulic fluid over long distances. High-pressure pipes would have to travel thousands of meters of depth to reach the Titanic, and any failure in the piping system or hydraulic compressors could cause the operation to fail, leaving it out of control and endangering both the Titanic and the recovery team. Number 5. Submarine balloons. One of the most intriguing proposals for recovering the Titanic involves the use of submarine balloons or giant lifting bags. This method, commonly used for rescuing smaller vessels or submerged cargo, suggests applying the same technology to one of the most iconic wrecks in history. However, while the idea seems simple in theory, the size of the Titanic and the extreme conditions of its location present nearly insurmountable technical challenges. The basic principle of this method is to inflate underwater bags attached to the wreck to provide buoyancy. These bags, made from materials such as Kevlar or reinforced carbon fiber, would be durable enough to withstand the crushing pressures at 12,500 feet depth. Deploying these bags at strategic points on the Titanic would require meticulous planning and the involvement of multiple remotely operated vehicles, ROVs, to properly place and secure them to the hull. The logistics of bringing hundreds or even thousands of these bags to the wreck site would be a monumental challenge, involving multiple support ships and an advanced underwater navigation system. Inflating the balloons also presents significant complexities. Air would need to be pumped from the surface through kilometers of resilient pipes, requiring strict control to prevent the bags from inflating unevenly. An uncontrolled inflation could cause irregular stresses on the Titanic's structure, distorting or even fragmenting it. Additionally, the process of lifting such a large and heavy object must be constantly monitored in real time, adjusting the air filling rates to maintain the stability of the wreck during the ascent. While this method has proven effective in smaller scale contexts, adapting it to the scale of the Titanic would be a Herculean task. The limitations of available materials, the logistics of transportation and installation, and the risks inherent in the fragility of the wreck make this approach, though fascinating, extremely complicated and costly to implement. Number 4. Lifting debris and parts. Cutting the Titanic into smaller fragments and lifting them in parts is another interesting proposal for recovering the wreck. This method aims to overcome the difficulties of lifting the entire ship by dividing it into manageable sections. Once sectioned, the parts could be transported to the surface using flotation bags or underwater cranes. While it seems like a more practical solution, the technical complications and associated risks are just as considerable. The first step in this process would be to meticulously cut the different sections of the Titanic using advanced robotic tools, such as hydraulic saws, plasma torches, and abrasive cutters. These tools would operate from autonomous or remotely operated submersible vehicles, as the depth of the wreck makes direct manual work impossible. However, total darkness, low temperatures, and the advanced corrosion of the hull make the work of these machines incredibly difficult. The tools would need to be powerful enough to cut through the ship's thick steel hull, but also precise enough to avoid further damage to the ship's fragile parts. A major challenge is determining the optimal points for the cuts. The Titanic is severely deteriorated, and cutting in the wrong areas could further compromise its structural integrity. Additionally, any cutting operation would require a detailed analysis to ensure that the sections are stable enough to be transported without collapsing during the process. This would involve mapping the wreck with precision, identifying the safest lifting points, and designing a cutting plan that minimizes the risk of damage. History offers a revealing example of the difficulties of this approach. In 1996, an attempt to recover a small section of the Titanic's hull, weighing 21 tons, ended in disaster. The diesel-filled balloons designed to lift the piece failed, and the support lines broke, causing the section to fall back to the ocean floor. This attempt, which cost $1.5 million, highlights the complexity and risks of attempting to lift parts of the Titanic. While dividing the Titanic into smaller fragments seems like a logical approach, the logistics, costs, and the risk of irreparably damaging the wreck make this method extremely complicated. Despite these challenges, the idea underscores human creativity and ingenuity in the quest for solutions to recover a priceless piece of history. Number 3. Freezing the Titanic with liquid nitrogen. The ice that sealed the fate of the Titanic could ironically be the key to its rescue. A revolutionary idea proposes to completely freeze the wreckage using liquid nitrogen, creating a solid block of ice that would encapsulate the ship and make it floatable as a cohesive unit. Although this approach sounds like something out of a science fiction novel, the logistical and technical challenges are as astonishing as the Titanic's own story. The first step would be to construct a metal mesh to wrap around the wreck, not only to protect its fragile structure, but also to contain the ice that would form around the remains. Designing and deploying this mesh at 12,500 feet deep is a challenge in itself. It would need to be strong enough to withstand the enormous pressures of the seafloor, yet flexible enough to conform to the deteriorated hull of the Titanic without damaging it. Next, large amounts of liquid nitrogen would be pumped to the wreck site. This gas, which reaches temperatures of -196 degrees Celsius, would have to be transported by tanker trucks to surface ships, where it would be stored in cryogenic cooling systems. From there, it would be sent to the ocean floor through specially designed pipes that could withstand both the temperature and pressure. One of the greatest barriers is the high thermal capacity of seawater. Freezing an object as large as the Titanic, surrounded by thousands of tons of water, would require an extremely efficient cooling system. Additionally, the sediments on the ocean floor could interfere with the even distribution of the cold, making it difficult to form a cohesive block. The entire process would need to be monitored in real time to ensure that the ice forms correctly and does not cause further damage to the wreck. Once frozen, the Titanic would become a solid block that could be raised to the surface. However, transporting such a large and heavy mass of ice would present its own set of challenges. The movement of this block could fracture if not handled with extreme care, risking the integrity of the remains. Although this idea is theoretically possible, the technology needed to carry it out at such depths is still beyond our reach. Number 2. Controlled explosion. The use of controlled explosions to fragment the Titanic into more manageable sections is one of the most controversial and risky proposals, Although it may seem destructive, the idea behind this method is to apply precise explosions to strategically cut the wreck without pulverizing it, allowing the resulting pieces to be raised more easily. However, the complexities of executing this approach at extreme depths and in such a delicate environment make it a risky bet. The plan would require placing specialized explosive charges at predefined points on the hull and other parts of the wreck. These charges, specifically designed to direct their force precisely, could be capable of breaking the thick steel of the Titanic without causing irreparable damage. Unlike conventional explosives like TNT, this approach would use shaped charges that concentrate energy in a specific direction, minimizing the impact on surrounding areas. However, practical implementation is extremely complex. Placing the explosive charges in the exact locations would require thorough mapping of the wreck, as well as advanced underwater vehicles to maneuver through the debris field. Additionally, the shock waves generated by the explosions behave unpredictably underwater, especially at extreme depths. These shock waves could reflect and amplify, damaging parts of the wreck that were not intended to be affected. Even with perfect execution, controlled detonations could have unforeseen consequences. The fragility of the Titanic, after more than a century on the ocean floor, means that small cracks or structural weaknesses could be amplified, leading to a catastrophic collapse of entire sections. Furthermore, monitoring the explosions in real time would be crucial to avoid mistakes, but this presents its own challenges in such a hostile underwater environment. Although the concept of controlled explosions has some methodological appeal, the technical barriers and associated risks make this approach one of the most dangerous and difficult to execute. The possibility of causing irreversible damage to the Titanic is likely to keep this idea in the realm of theory for now. Number 1. Lifting with magnets. The use of magnets to recover parts of the Titanic presents a fascinating idea based on the properties of magnetism. The idea is to use powerful electromagnets to attach to the ferrous pieces of the wreck, such as steel plates from the hull or structural components, and lift them from the ocean floor. This approach offers a non-invasive way to recover fragments of the ship without causing significant damage to its structure. However, the challenges associated with this method at extreme depths are formidable. The magnets needed for this task would have to generate magnetic fields strong enough to lift pieces weighing several tons from a depth of 12,500 feet. The energy required to operate these magnets would be astronomical, and the conditions of the seafloor complicate their functioning even further. The pressure at the ocean floor, which exceeds 5,500 psi, would test not only the strength of the magnets, but also the durability of the electrical cables connecting them. Additionally, the corroded surfaces of the Titanic could hinder the adhesion of the magnets, compromising the effectiveness of the method. A critical aspect would be precise control. The magnets would need to be able to adhere and release selectively to avoid unnecessary damage to other parts of the wreck. This would require a sophisticated control system that could operate in a dark and debris-filled environment where any mistake could cause irreversible damage. Furthermore, the risk of fractures or collapses in the fragile sections of the hull represents a significant obstacle. Handling large pieces could alter the stability of the wreck and cause further damage. While the idea of using electromagnets is innovative, the current technological and logistical barriers make this method more of an exercise in imagination than a practical solution. However, it represents a creative approach that could inspire future technological advancements for recovering historic wrecks like the Titanic. Thank you for joining us on this journey through the incredible proposals to recover the Titanic. Should we attempt to raise this icon or respect its rest in the ocean? Leave us your opinion. We'll see you on the next adventure into the unknown. See you soon.